Bien, bonjour à toutes et tous.
Good afternoon, everyone. Welcome to the auditorium of the Cité des Sciences et de l'Industrie for this conference dedicated to extraterrestrial communication and to the search for intelligent life in the universe. My name is Soufiane Oncheri. I'm a scientific mediator at the Cité des Sciences et de l'Industrie, and I'm very pleased to be able to be with you throughout this afternoon. I'm now going to, without further ado, give the floor to Brigitte David, who is a scientific mediator at the planetarium of the Cité des Sciences et de l'Industrie, who is going to talk to us about the origin of this event. Thank you very much, Soufiane. Welcome, everyone. So, the origins of this extraterrestrial weekend is as follows. There is a researcher called Douglas Vakosh who works at METI International. METI is Messaging to Extraterrestrial Intelligence. And he is in San Francisco. And 4 years ago, he left San Francisco, he took the plane, and he came to Paris. And he came to visit our team at the planetarium. He saw our show, and he talked to us about his research. He also told us as well that he had done a conference on planetarium research in San Francisco. He spoke to us about this topic, and he proposed this idea so that we could design our own show at the planetarium. And so, the theme is the search for life in the universe, life that is capable of communicating. And it is also about message dispatch trials into the universe. He mentioned all of this, and he also spoke to us about a person called Florence Roland-Cerceau, who is the vice president of METI International. She's in Paris, and she's a researcher, astrophysician, historian, and a historian of SETI, which is a search for extraterrestrial intelligence in the universe. And she became our scientific counselor or scientific advisor, which was great because she's in Paris. And we're very fascinated by this topic, and we're fascinated by Douglas's enthusiasm. So we thought this is great because at the planetarium, in the show that we're currently designing, there is a series which is called History of Astronomy. And so we thought, right, well, we'll do a show that will explain the evolution of this reflection, of this thought. That is to say, the idea of looking for life elsewhere, in habitable zones. Perhaps there are people that are trying to communicate with us. And therefore, we are trying to design a show that really goes through this philosophical and scientific idea, and we've created a scenario that goes from the philosophers from antiquity right up until current research. I will talk to you more about the show at the end of this afternoon to keep the suspense, but what I wanted to say to you is that Mr. Douglas Vakosh, when he worked at the SETI Institute before going to METI, he had a very surprising business card, and his business card said Director of Interstellar Messages. And that's quite rare to see on a business card. So, Doug, can you hear me, Doug?
Je vais vous présenter Doug.
I'm going to introduce Doug. Doug, can you talk to us a little more about your business card, please? And can you also talk to us about, if you don't mind, the work that you did when you were here, and also about your new organization, METI International? Thank you.
Thank you very much, Brigitte, for welcoming me this afternoon. And again, as you said, we have been in discussions for several years. It is really an honor for working with Florence Roland-Cerceau, our vice president, and the planetarium, because the work that you do here provides a way to really communicate to the broad public how it is we go about this search, why it's important, what it means for us. And so we're really honored to be able to participate in this event that you have today. My background, as you mentioned, was working with the search for extraterrestrial intelligence. So this is a project, now it's worldwide, where astronomers use radio telescopes, the same telescopes they use to understand stars and galaxies, but now to use them in a different way, which is not to look at the information coming into Earth from the natural objects, like globular clusters and observing planets in our own solar system, but to look for signals that are distinctly artificial, that indicate that there are other civilizations out there sending us the messages. And so my work at the SETI Institute for 16 years was to prepare for the day that we may receive a message. So as the director of interstellar message composition, I would work with a team to design the messages we may someday send, to discuss the process. How do we even go about this? How do we create a message that would be understandable to a civilization that, I'm sorry, I have to say, they won't speak English or French or Chinese. So we have to come up with a language they'll understand. So that was the work I did for many years at the SETI Institute, preparing for the day that a signal comes in. And SETI, as a scientific enterprise, has been going on now for 60 years. But so far, we haven't heard anything. And so what happens if every civilization out there is doing what we are, simply listening and not transmitting? That was the foundation for creating METI, Messaging ExtraTerrestrial Intelligence, where we reverse the process and send powerful, intentional signals to other stars to let them know we want to start a conversation. And so really, there are complementary ways to try to make contact. It's important that we continue to do SETI. Our organization, METI International, also supports SETI projects that look not just for radio signals, but very brief laser pulses, a new way of doing SETI that's developed over the last 20 years. But our primary mission and our namesake activity is to message, to let the extraterrestrials know that we are here and we want to make contact.
Alors, j'ai une autre petite question.
So I have another quick question, Doug. When we take a look at the universe and the immense nature of the universe, there are tens of planets that are thousands of light years away from us. And so if we send a message into the universe, in concrete terms, what hope can we have? What is the concrete objective? So, for example, do you think that if there is some life not too far away, do you think that we would be able to receive a response within a generation, within a few generations? In concrete terms, what is your hope and what is your objective?
Well, in concrete terms, the next target star for our transmissions is the nearest star to Earth, Proxima Centauri. This is a red dwarf star that is just over 4 light years from Earth. That means it takes light and radio 4 years to go from Earth to that star. And if there are aliens there, they're interested in having a conversation, if they send a reply back immediately, it'll take a little over 8 years. So that's the best case scenario. But the reality is, for that to work, practically speaking, it means all of the stars have to be populated. And so I think realistically, we may need to be transmitting to stars much further away. Maybe it's a star that is tens of light years, hundreds of light years, maybe even thousands of light years away. And so that is the greatest challenge of METI, to embrace a long-term project, to look toward the future and to make a commitment to try to make contact, knowing that the results may not come in our lifetimes, but may come in for future generations. And so that's one of the reasons it's so important for us at METI International to have an engagement with organizations that are involved in education, because it may be the young people here in this auditorium today and watching on YouTube that are the ones who are going to be around to get a reply.
Et j'ai une autre question.
And I have another question, and this is my final question. Doug, it's a personal question. What are the origins? Where did this desire to want to do this research come from? So where did the idea come from? What was the source of your enthusiasm? Because you came from San Francisco to come and see us here in Paris. It's not next door. And I just wondered, what is the source of all of this dynamism and this enthusiasm?
You know, I grew up in the 1960s, and so that was the decade that in the United States, there was a tremendous push to get to the moon. it was a chance to commit to a large scientific project as a nation and to move forward and to accomplish that goal. And so as I was growing up, that's what I saw as a possibility. And then at the same time, during the 1960s, the first SETI projects were beginning. We were now looking for life beyond Earth. And so for me, the initial appeal, the earliest appeal was simply wanting to understand everything. The beauty of searching for life in the universe, for someone who's interested in science like I was, you get to study all of the sciences, astronomy, geology, biology. And then as I grew older, I realized also psychology and history. So this is one of the things that keeps me involved. When I was young, I was most interested in knowing what might the aliens be like. But what I've realized over the years is that simply in the process of searching, of committing to a project that may take generations to succeed, we learn a tremendous amount about ourselves and we develop as a civilization.
Eh bien, c'est passionnant. Merci.
That's very, very interesting. Thank you so much, Doug. We will hear from you again during the roundtable. So, we are now going to show a video that we have shown at the planetarium, and this is about the planetarium chairs. I'm going to have you take a look at this. It's nothing to do with aliens, but it's worth seeing anyway. And now I'm going to give, and after that, I'm going to give the floor to Soufiane. Thank you very much, Doug.
Thank you.
C'est marrant, on voit vachement bien la station spatiale quand même.
So we can see the space station there. I think I'm in the wrong seat. The person next door doesn't seem very happy. No, I think that's Soufiane, who is just having difficulty breathing through his mask. And what George Lucas doesn't say.
Alors, Jean...
So, I am just going to remind you very quickly to think about ensuring that you hand back in your interpretation headsets when you leave, and do not hesitate to go and look for one if you need an interpretation headset. So, now we are going to hear from Florian Philippot, who is a PhD student in astrophysics at the Observatoire de Paris. Florian Philippot is going to talk to us about his research on exoplanets. Florian, you have the floor. Do you have a microphone? Can you hear me? Brilliant. It's all in order. Good afternoon, everyone. My name is Florian Philippot, and my work as a PhD student at the Observatoire de Paris is to work on the research of exoplanets. And so today, what we mean by this is the search of life beyond Earth. And so I'm going to give you some details about my research and how we're going to detect extraterrestrial life forms using other means. So to begin, this pointer does not seem to be working. Oh yes, it is, sorry. So to begin, let's just go over very quickly what a planet is. A planet is first and foremost an object that orbits around the sun. And to orbit means it's the trajectory of the planet around a star, and therefore a planet is an object that turns around its star, such as the moon, which turns around the Earth, which orbits around the Earth, which is not seen as a planet. However, this definition corresponds to asteroids and comets. So how can we make the difference between a planet and a comet? And well, we can do that based on their shape and mass. So from a certain mass, an object will take a sphere's form, and as you can see on this image, the other planets are a round shape. And if you've taken a look at planets, they have different shapes. Thank you. And so this was the definition. That was the definition until 2006. However, in 2005, a new object behind Pluto was discovered, and this object was called Eris, and was a size that was similar to Pluto, and therefore we wondered, do we add it as a 10th planet, or do we change the definition of a planet? And the International Astronomical Unit made this choice and added a second rule to define planets, and this is a planet that will clean the vicinity of its orbit. What does this mean? So through the trajectory, or on the trajectory, there should not be objects that are massive, that are big, and that will impact the trajectory. There is no massive object around Earth, for example. However, Neptune is a lot bigger, and so we moved Pluton and create a new category that we call dwarf planets that we added, such as Ceres and others that were added to this category. And so when we talk about exoplanets, we're talking about planets. And we have two types of planets. We have first and foremost the telluric planets, which are closer to the Sun. And so there is a rocky surface on these planets, so we can't land on those surfaces, unlike the second case, which are gaseous planets. And those gaseous planets, such as Saturn, for example, are mainly comprised of gas, and if you tried to land on the surface, then you would not be able to penetrate the atmosphere, and you may be crushed by gravity. So we have two major types of planets with subcategories of giant planets, such as Neptune and Uranus, which have a large core, and then we have other planets, such as telluric planets, and the difference is their size and mass. And we have telluric planets that are a lot smaller than gaseous planets. And you will see later on that Earth is a lot smaller than Jupiter, and this impacts research of planets such as Earth. And so here you have Earth, 12,000 kilometers. But if we compare it to a gaseous planet, in particular Jupiter, well, this is what it looks like to scale. So Earth is more than 10 times smaller than Jupiter. And you can see here that Earth is the side of the red mark that you see here on Jupiter. However, Jupiter, which is one of the biggest planets, if we compare it to the Sun and other stars, we have a ratio of 1 to 10. So here we see that the Sun is 10 times bigger than Jupiter, so 100 times bigger than Earth. And so if we think about the Sun as being a melon, for example, Jupiter would be a chickpea, and Earth would be a grain of sand. And so we have objects that are very different in size, and this will have an impact on our research. It's very easy to detect a star because they're big and shiny. A planet the size of Jupiter, it is more difficult because they're smaller and they're not bright planets. And planets like Earth, it's very difficult to detect, and we'll talk about this later. So, since we have these very diverse sizes, there are distances as well that are not always easy to understand and apprehend in the universe. And so these distances are so vast that rather than talking about kilometers or billions of kilometers,
on va utiliser de nouvelles unités.
we use another unity, which is the astronomical unit. So what is this? Well, it's a term that I'm sure you've heard about. You will have heard 1 UA, 2 UA, or 1 AU, 2 UAs. And what is this? It is the difference between Earth and the Sun, or a distance of 150 million kilometers. So rather than saying that a planet is 150 million kilometers away, we will use terms such as 1 astronomical unit, 2 AUs, or 3 AUs. And so, for example, if we want to compare the planets of the solar system. So we have Earth, which is 1 AU. Then we have Mercury and Venus that are closer, and therefore that are less than 1 AU. And then we can see that there's a big gap between Mars and Jupiter. So we switch from telluric to gaseous there, and then we can see that we can go up into greater astronomical units. And so, for example, I will just talk to you about these sizes very quickly. So we have, for example, Earth, which is a step away from the Sun. So the Sun would be here. And then Jupiter would be 5 steps away. So I'd have to take 5 steps. And I'm increasing the distance between me and the Sun. So if I want to go to Neptune, then I will have to take 25 steps, and I will probably be outside of the auditorium. And so this is just our solar system. Now, if we're talking about exoplanets, so outside of our solar system, then the distances are even greater. You will have heard the term earlier, light years. So what is 1 light year? It is the distance that a light particle, a photon, will travel. And in 1 year, that photon will have traveled 1 light year, the distance of 9,460 billion kilometers. So just to go back to the idea that I mentioned earlier on, so if you were to make some steps to reach that planet outside of the solar system, then you would end up in Marseille. And so here we have the star Proxima Centauri. I am talking about it because it's the closest star to the Sun. And this is 4.3 light years. And that means that to get there, instead of walking to Marseille, you would be walking to Moscow. And so that distance is a lot greater. And this is would be problematic as it relates to the study of life beyond Earth, because if we found exoplanets that are habitable, they are very, very far away, and those distances are so great that it would take us a very long time to even communicate with them. A message to dispatch a message to that planet, it would take more or less 8 years. And so we talked about planets. There's something else that's very interesting and that's very important for exoplanets, stars, because they orbit the planets. And so a star, unlike planets, are gaseous like Jupiter, but they produce their own light thanks to nuclear fission reactions. So basically the stone is made mostly of hydrogen, and given the high levels of gravity, the hydrogen atoms can fuse together to create a helium atom, and that will provide energy. And by freeing energy, it releases heat and light. And that's not the case for Jupiter or for Earth. And on this diagram here on the right-hand side, we can see that there are lots of different types of stars. We have, for example, our Sun, which is a yellow dwarf planet, and which is the average size and average temperature for stars. In addition to the Sun, there are other stars like the red dwarf, the Proxima Centauri. These are smaller, cooler stars, or blue giants, which are a lot bigger and a lot warmer than the Sun. And we think that in 5 million years, the Sun will grow to become a red giant. And these blue giants will become smaller. And so what we're interested in mainly are the objects that are found in the principal sequence. These are stars that are not very active. That means that there is not too much matter that is ejected. They're stars that we know very, very well, so they're easier to manage. And that's it. And in addition to that, we are interested in solar stars that are quite close to us. And so in the galaxy, so stars that are roughly 100 light years away from us. Beyond that, it would become more challenging to study. So, to summarize, an exoplanet is a planet which orbits around a star but which also orbits around a star that is not the Sun. And these exoplanets, how can we observe them? Because they're very far away. Well, if you look at Jupiter, then you can just do that with a telescope, not a particularly high-performing telescope either. And you will have an image that is similar to this one, and you could observe the planet. However, if you want to do the same thing with a star, so the star, for example, that we discovered the first exoplanet, then the image will look like this. And this is a big professional telescope that is used in an observatory, and this would be the image that you would see. But the planet is actually inside this yellow circle here, so you cannot see it directly with a telescope. Therefore, we need to use more advanced technologies to detect and identify planets that orbit this star. And in order to do this, we won't use our amateur telescopes. We'll use a lot bigger telescopes with mirrors, such as the very large telescopes, rather, VLTs, that are located in Chile, where we have 4 telescopes that are 8 meters, have 8-meter diameters. Or we use spatial telescopes, such as the Hubble telescope here that we see on the right-hand side, that was sent in 1990 and still continues to function and is able to identify exoplanets. And so to detect exoplanets, we have 2 methods. We have methods that are indirect. That means that we won't directly detect the planet. We can't observe it. However, we can observe the impact that the planet has on its star. And so we have a number of indirect detection methods. And today I'm going to talk about the 2 main ones, transit and radial velocity. And in addition to the indirect messages, we have the holy grail of observation and exoplanets, and these are direct detection methods. And this means that we're able to directly observe the light of the planet, which obviously requires a lot of technology and image correction. And let's start by talking about the transit method. It's quite simple. What we observe a star, and if a planet passes in front of the star, the light that we see will diminish like this. And you can imagine a lamp, and if there is a big moth that goes in front of the bulb, you see that the light will dim. And it's the same thing here when a planet passes in front of a star. And depending on the period, that is to say, the number of days or years that the planet requires to orbit the star, then this dimming of the light will continue. So imagine Earth, then there will be a dimming of light every year. Let's take another example. A planet that requires 4 days to orbit its star, then every 4 days we would see this dimming of the light, an increase of the light, a dimming of the light, and then an increase of the light. And this dimming of the light also depends on the size of the object. So, for example, Jupiter will cause a light dimming that is a lot more significant than Earth. So with this method, it's easier to detect a planet like Jupiter, which is close to its star, than a planet such as Mars, for example, which is not very big, which is further away from its star. And so what are the advantages of this method? Well, they give us the size of the planet. But we don't have any information about the mass, and that's very important to know what type of object we're dealing with. And then also, this is really limited to small distances, because if we get too far, then the dimming of luminosity will not be good enough to detect using the technology that we have. A second method of detection, which I appreciate because it's the one that I use in my work, and this is the radial velocity method. This principle is based on the Doppler-Fizeau effect. It seems quite complicated, but I'm sure you've already tried it. This is what happens when you go past an ambulance or a motorcycle, for example. You hear a sound that is similar to this. And so what happens for this sound? What happens to create this sound? Well, the motorcycle or the ambulance emits a sound. And when the object comes closer to you, the sound is contracted. And when it gets further away from you, the wave is dilated. And so then it leads to a decrease of the frequency. And it's the same for light. Light is also a wave. So if you can imagine the same motorcycle arriving at a speed which is similar to the speed of light, you would see it as blue, but when it gets away from you, it would become red, because this depends on the contraction of the light waves. And so this is exactly what we see for stars.
Comme par exemple la Terre tourne autour de...
A planet like Earth orbiting around the sun. Well, the planet attracts the star and the star attracts the planet, but has a small rotation movement of the star that is detectable thanks to this Doppler effect. It goes towards the red when it goes further and blue when it's closer. So you see it does this movement. You can see it on the screen, and it gives us information about the planet. If there is a repetition of this pattern, it means there's one orbit. For example, with the Earth, there's this pattern once every year, and the further you go, the more time you need to observe and get concrete information about the planet. Now, about the mass. A very massive planet will have a bigger impact on the star. For example, Jupiter attracts the Earth, the Sun, then the Earth would attract the Sun. So it gives information about the mass and distance, but we don't have any information about the ray. And it's hard to observe anything that is further than 5 astronomical units. You need 12 years to do this kind of observation. We've been observing exoplanets for about 25 years now. So we have some good informations about planets that are further than Jupiter at this point. The last method now, it's direct imagery. You can observe directly what's happening. You can observe a whole system using adaptive optics. So you can regulate the information that is linked to the atmosphere or the instrument. And there's an object called a coronagrapher. So you use this, what I'm pointing at on the screen, to mask some of the flow of the star, so you can see better the planet that is at the periphery of the star. So you see this telescope on screen. It's usually sent at the end of the year to use direct imagery to find exoplanets and maybe find planets that are similar to Earth. So this is the kind of picture you get with direct imagery. Here the disk is the star hidden by the coronagrapher, and you can see the different blue points orbiting around the star. So these pictures were taken for days and years, and you can see what's happening here on the screen. It's a bit similar to the solar system, if you want. So there's the star in the middle and the planets orbiting around it. And that's very interesting because you observe directly the planets. You get information about the atmosphere, about the distance to the star. Here you've got a scale on the screen. You can see the units at the bottom of the picture. So you can say whether it's 10 or 20 astronomical units. And you can see that these are massive planets. They're quite young. The Earth would be around here if it was the solar system, so it wouldn't have been detected. You can only detect planets that are further from the star. So you can see that there are many exoplanets. Here is a map of exoplanets according to their distance and their mass. Sorry, I'm struggling a little bit with this thing I'm using to point at the screen. So you can see the radial velocity in green and the transit method in red. You can see these are massive planets that are far from their stars. And if you compare it with the planets of our solar system, you can see that we are still struggling to detect some objects in our system. So we've got information about Mars and Mercury. But for Jupiter, thanks to radial velocity, we detected some planets that are maybe close to Jupiter. And for the Earth, we have detected a few thanks to orbital to another methods that can only be used to observe the planet once. But radial velocity and the transit methods are instruments that are used very often. It is used to observe planets like Venus, for example. There's something that we are interested about when we study planet systems. It's the habitable zone. What is it? It's a zone where temperatures make it possible to find liquid water on the planet, if there is liquid water. So here is the solar system. You see in blue the habitable zone of our solar system. Earth is in that blue line. We have liquid water on Earth. But this habitable zone is not fixed. It really depends on the star that is in the system. The hotter a star is, the further this habitable zone will be, because temperatures can't be too hot to get liquid water. So Gliese 581, on the left, you can see it. You've got a system with 6 exoplanets. The habitable zone is actually closer to the star than Earth. It's 1 astronomical unit for Earth, but for Gliese 581, it's 10 times closer. And this is because it's a red dwarf, so it's a star that is not as hot as the Sun. And for example, maybe you wonder why there are letters on the screen, E, B, C, G, D. It's because of a notation system. For those of you who don't know, when we discover a planet system, we add letters in the order in which the exoplanets were found. So the first one was the B, then the C, third one D, etc. And there are 2 planets here in the habitable zone. However, the G planet hasn't been confirmed yet. We're not sure that's where this exoplanet here is. But there should be 2 planets in the habitable zone, which means there could be liquid water on these planets. However, temperatures are not sufficient. If you take a look at the solar system, you can see that Mars is in the habitable zone and Venus is almost in the habitable zone. However, on Mars, water is only found in ice form. So temperatures is not everything. We have the greenhouse gas phenomenon on Earth that warms the planet, and without that, there would not be positive temperatures on Earth. The temperatures would be -5 degrees. And that explains the temperatures on Venus. In Mars, well, maybe there used to be oceans at the beginning of the history of Mars, but everything was eroded by solar winds. So it was impossible for liquid water to remain on the surface, and now it's only ice. So the habitable zone is something positive because there could be life on these planets, but we need to study these objects a lot more. Now, to sum up what was discovered so far, the first detection happened in 1995. Mayer and Kellos found the first exoplanet orbiting around a star similar to the Sun. And they got the Nobel Prize in Physics in 2019 for their work. For 25 years now, we've been looking for exoplanets, and we have discovered 4,761 exoplanets so far. And in this huge number of exoplanets, we discovered that there were objects that are very different to what we know in our solar system. These new objects have completely changed the way we understand the mechanisms of formation of planet systems and solar systems. We thought that planets did not really move. They remained the same for millennia. However, now we understand things differently. And we have used this information to modelize our own solar system. So it really is a summary of what we have discovered. So what have we found over the past few years? So the first planet discovered, 51 Pegasi b, was a hot Jupiter. It's what it's called. What is a hot Jupiter? Well, it's in the title. Its mass is close to Jupiter, but it's very close to its star. So temperatures are really hot. The closer you get to your star, the hotter it gets. The closest one to its star was at 0.025 astronomical units. And we already said that some planets could be very close to their stars. And if the star is similar to the Sun, you can imagine how hot the temperatures are. And it helped us understand planet systems. So what happened is that these planets formed at the same distance as Jupiter and then got closer. So if there was a planet in the habitable zone that was similar to the Earth, it may have been ejected from the system and it's not there anymore. So there are systems with hot Jupiters and hot planets, but it's not interesting in terms of researching for extraterrestrial intelligence because there are no planets similar to the Earth in these systems. Other interesting objects, the super Earth. You notice that our names are very original in astronomy. So what are these? Rocky planets, but they can be 2 times bigger and 10 times heavier compared to Earth. So they are bigger and easier to detect than Earth, for example. There is these are rocky planets, and potentially there may be liquid water on the surface if temperatures are right, if there is greenhouse gas effect, and so on. So these are candidates to find intelligence, extraterrestrial intelligence on these planets. Other interesting names, compact systems. What are they? It's a planet system with different planets orbiting around a star, and they are very close to each other. For example, the TRAPPIST-1 system. Well, it was very famous because 7 planets and with a size similar to Earth were found at the same time. And all these planets are orbiting a star in this very small zone. Here it's at scale, so it's very close to the star. It's around a red dwarf, so it's actually a lot smaller than the Sun. So, and there is a rocky planet here, planets E, maybe planet F and D. These 3 exoplanets are in a habitable zone, so there may be liquid water on these planets. Another characteristic, these are synchronized. What does it mean? Like the moon, they always show the same side to their star. So it would mean that one side of the planet would be desertic and the other one may be frozen, because only one side of the planet is always facing the sun, the star in the system. Now, let's talk about other objects. The mini Neptunes. It's similar to Neptune, but smaller. So there's a rocky core, ice, and an atmosphere made up of hydrogen and helium. Or hot Neptunes, similar to Neptunes, but hotter. And there are also rogue planets, wandering planets. They do not orbit around a star. These are objects that have been ejected from their system or which have just formed just like a star would. So there's gravity becomes such that there's a nuclear reaction that is started, and they can just grow up to the size of Jupiter, and it's a possibility. There are also binary systems. I'm sure the Star Wars fans will understand. It's like Tatooine. A planet is orbiting around 1 or 2 or 3 stars. Sometimes a planet orbits around 2 stars that are also orbiting around each other, or around one star that is orbiting around another star. And another interesting thing, it's not planets, it's the red dwarfs. They are between planets and stars. There are nuclear reactions, a bit of light and heat, but they're not big enough to have bigger reactions like a star would. And I mentioned before studies of atmosphere of these exoplanets, and that's quite interesting, because if we want to research for extraterrestrial intelligence and we would get information from the atmosphere, it's hard enough to observe exoplanets. So imagine observing what's happening on the surface. So we can use direct imagery, the light spectrum emitted by the planet, or the transit method can be used. So when a part of the star is absorbed by the planet, and what is absorbed thanks to molecules can be detected in the spectrum. And to do that, and so that we can detect it, you need planets with an important atmosphere like Jupiter or Neptune. A planet like Earth would be undetectable with such a method. So with our new missions, we will try to improve the sensitivity, so maybe we can find planets with an atmosphere that is similar to Earth. So when you study atmospheres, you have spectrums like these with different data, and we use models to evaluate the composition of the atmosphere, and we get some information about the molecules that are in the upper part of the atmosphere of the planet. And you can see there was absorption due to water, or here due to ammonium. This was the transit method. I'm sorry I didn't say that before. Here, with imagery, you can observe other molecules, spectrums that are more complex. Here, there's an absorption because of iron, or here because of water. So thanks to these different spectrums, we were able to observe carbon dioxide or different metals, And hopefully, maybe we can observe ozone, for example, what we know from our atmosphere, or maybe traces of radioactivity that was caused because of a nuclear war on this planet. That would be an interesting type of information to get. But obviously, we need to relativize about what we can do on our own planet. Now, I would like to talk about Proxima Centauri. It's in our neighborhood. It's the closest star to us. Around Proxima Centauri, we detected 2 planets, Proxima B and Proxima C. Maybe another one, but it's not been confirmed. One of them is in the habitable zone of its star. You can see that the mass is similar to Earth. It's very close to its star, but Proxima is a red dwarf. And like we said before, the habitable zone for a red dwarf is closer than in our own solar system. So there could be liquid water on the surface of this planet, and we are looking for biosignatures during the different missions that observe these stars. So this is the system that is closest to the Earth. It's easier to observe, and it would be easier to communicate with them if we were to find intelligent life on this planet. So this planet in the habitable zone is similar to the Earth, and there could be liquid water on the surface. However, the problem with this kind of planet is that these planets are very active. There are many X-rays or particles that are emitted, and maybe the surface of the planet is completely radiated. However, if there's an important magnetic field, just like on Earth, and the atmosphere is dense, there could be life on this planet. Like we said before, it is very far from us, although it's the closest one to us. So the probe that was sent for observation that I mentioned before, New Horizon, would need 23,000 years to get to Proxima Centauri. So we're not about to hear back from it. So there's still a lot of uncertainty about how we could get there, how we could communicate with them. There are new programs being developed to travel faster, but we wouldn't hear from them for a while. So what are the goals for the future in terms of exoplanet research? First, better understand the different planet systems. Like I said, the more we are detecting planets, the more we know about systems, about giant planets, about history. And we really hope that we can detect planets similar to Jupiter, or the Earth, or Venus, or Saturn. And so we would see if our system is unique in the universe or not, or if maybe there could be traces of intelligence, extraterrestrial intelligence on other planets. Also, we are now looking for exomoons. There were detections that were not confirmed. We are looking for moons, so objects orbiting around a planet, and it would be very interesting because with the moons of Jupiter's, we think that there may be life on the water of Ganymede and different Jupiter moons. Jupiter is a gaseous planet, so there could not be life as we know it, but with some of the moons, there could be temperatures that would make it possible to have liquid water on the surface, maybe even an atmosphere. There are many parameters, but it's quite interesting to study. And for the future, we are trying to be able to better observe the atmosphere of exo-Earths. to look for signs of life on the surface of these planets. Thank you very much.
On va prendre... Merci beaucoup, Florian.
Thank you very much, Florian. I think we have some time for a few questions, so please do not hesitate. If you do have a question, we're going to have the microphone go around the room. Yes, we have a gentleman over there with a question. The interpreter apologizes, we did not hear the question.
Oui, excusez-moi.
Monsieur t'a posé.
La
Merci.
question,
So the question was, what do we do if a planet has an orbit which is not aligned with ours? So, for example, using the transit method, they have to be aligned, very well aligned. So, for example, if we orbit the Sun like this, if the other star orbits like this around their star, then it will never go between the star and the planet. And in that case, we would not be able to detect it. And something I didn't mention, the transits concentrate on planets that have an orbit which is more or less in line with ours. And that is a restriction for our study. And we have the same thing with radial detection, because if the planet orbits like this, then the star has a movement like this, and that means it will never become closer or further away from us. And so these are problems, which means that we can't observe. But there are other methods, like astrometry, for example, that studies the movement towards us, but also a movement that is perpendicular to us, that would enable us to detect these planets, which are... These methods are still in development, but this is a method that exists to detect exoplanets. Thank you very much. Are there any other questions? The interpreter apologizes, but we cannot hear the question.
de manière...
Excusez-nous, parce
Oui,
qu'on
pardon,
est
il faut que je
rediffusé
répète.
en fait en direct sur...
So just to remind you, we are broadcasting this live on YouTube. So can you please repeat the question? Well, the question was, can we focus on specific zones in the galaxy to look for planets? And the answer is, well, we don't have much choice. As I was saying earlier on, the stars are in a... They're no greater than 100 light years away. It would be much more difficult to study planets that are further away. And so we concentrate on small planets, roughly 100 light years. And
On a observé une zone vraiment infime de la galaxie.
so we are looking at a very specific zone in the galaxy. The further we get away, the more difficult it is for the studies. We were able to detect further planets with other methods, but it was a lot more challenging. Okay, we have one final question. Please do not hesitate if you do have a question in the room. So just bear with me one moment. I'm going to just run across the room very quickly to see if we can get the microphone to her. I know nothing about this, but I understand that you think that we can find life on planet, but for that there has to be water. Is that correct? And so I wonder if this is not an Earth-like vision of things. Can we not consider that there might be maybe life that doesn't require water? Yes, potentially. And that's the issue with the habitable zone. So we're talking about forms of life that we know on Earth. And so the life as we know it requires water. But yes, we can imagine other forms of life. On Titan, for example, one of Saturn's moons, there are methane lakes, methane rivers. There are some theories that say that maybe life forms would develop based on metal or methane rather than water, for example. And there may be life forms that develop using silicon, for example. And so our definition of the habitable zone is very restrictive. So, indeed, as soon as we are able to observe an atmosphere, we do it. And if we find a trace of a molecule that is unexplainable, I think that this would lead us to question ourselves and imagine perhaps a life form which is completely different to ours, which is not impossible. But yes, this is a limitation that we are having to work with now. We have one final question here. We already have this on Earth. When you look at the oceans, there are nozzles that emit types of lava, and in those, in that lava, there are forms of life. And so, in concrete terms, these are living particles, or particles that we can consider as being living, that don't require oxygen. Yes, however, there is oxygen in water. But that is true, that in the missions to Ganymede, for example, Europe around Jupiter, there is a glass crust and an ocean underneath it. Then, yes, we look for forms of life or bacteria, for example, in this ocean, because we think that it is perhaps in contact with the core of the moon, and that could perhaps release elements that are required for life. And so, yes, there may be life forms that are able to develop in hospitable zones, or in hospital as relates to Earth. And so, yes, there are other forms that we can envisage that are difficult to study. So, for a planet that is covered with ice, maybe the life form is below the ice, and with the technology we currently have, it's impossible to detect that. But yes, this is something that we have envisaged. Okay, so we have one final question that comes from the chat. So, and I think Mark has the question. Yes, can natural satellites also have natural satellites? So, moons of moons. Well, this is a theory that came out a few years ago, 1 or 2 years ago. I think there were articles that came out about this, moons of moons. And indeed, some theorists think that, yes, there may be some satellites that form around satellites. However, most models that we have at our availability consider that this would not be very stable, and therefore a moon that orbits a moon, so a moon, would either be ejected or collide with a planet or another satellite. But yes, some models have envisaged this, indeed. Thank you very much. Thank you once again. Thank you very much for all of your questions. We are now
Avoir le plaisir d'assister.
going to hear from Maison Gamma. Maison Gamma is a collective of students from the École Estienne, and they study applied arts and creation. And so I'm going to invite the members of this collective to the stage. So we have Emily Salfati, Léane Bokis, and they are going to present their project. We also have...
Bonjour à tous.
Good afternoon, everyone. So we're Emily, Léane, and Khalid. We're 3 digital designers and creators, and we're talking about fashion, contemporary and future fashion. So all 3 of us create a collective, Maison Gamma, that you can see here. And we are hyper-prospectors, and we think about the clothing of the future. And we do this using interdisciplinary methods and techniques, and we're looking to think about the next iteration of fashion. And so here we have highlighted a movement between fashion creation and textile innovation. And this is presented using different fabrics, but also digitally using different creators. And we have a technological approach which really inspires us. And we're talking about the relationship we have with our clothes, but also their method of production and their use. So through clothing, we are demanding a harmonious relationship with the environment. And to conceptualize this, we used the knowledge of David Fossé, who is an astrophysicist, and he was the chief editor of a review, Ciel et Espace, but also a researcher of exoplanets. And he, in his research, presents exoplanets and their artistic vision. And so using this book, we took our inspiration from this book. So in accordance with his intuitions, in a far away future, in 30,000 years, we will perhaps be exploring exoplanets. And based on this, we imagine a time where exploration of exoplanets will be possible. And perhaps wearables will enable mankind to explore unknown and hostile environments. And so to define what an exoplanet is, it's a planet that is located outside our solar system and which gravitates around another star, which is the Sun. And so exoplanets, the closest that we know is an exo-Earth, that is to say an exoplanet whose characteristics are similar to that of Earth, and that is Proxima b. And it is 4.2 light years away from Earth in the Centauri constellation. And we imagine that it will be probably explorable in a few tens of thousands of years. And so what we thought was interesting with the exoplanets was that they offer new constraints, new territories to explore and to discover, for which we may have to adapt ourselves. And we imagine the different types of clothes for this. And on the other hand, our approach is part of the continuity of the history of fashion. In the 1960s, large designers such as Paco Rabanne, Cardin took inspiration from the spatial imagination in the context of the Cold War. But now it is taking on a new meaning in the current context, in particular with the conquest of Mars, but also the Moon and the satellite orbit, and also the research of resources that highlight this interest in discovering the universe. And we can also observe a certain fascination of large personalities such as Thomas Pesquet, for example, or Elon Musk, who demonstrate this devotion for the space imagination. And so we rely on scientific diagnostics, astrophysicians and specialists of spatial science to imagine the collections of clothing that will be adapted to the potential future territories. And these data is the starting point of our fiction that we're going to present to you, and also participates or contributes to its credibility. These exoplanets are not just a decoration or a backdrop. They have geographical characteristic and climatic characteristics that are very important and sometimes quite extreme, and they inspire us to change the relationship that we have between the body and clothing and its environment. And so using these new constraints of exoplanets, we feel a liberty, a freedom. It's a catalyst, a creative catalyst that enables us to go beyond ordinary vestimentary code or clothing codes by thinking about works of science fiction, such as Distill in June, which is a garment which recycles bodily wastes to make them consumable in a hostile environment. So this is a Coret 7b. It's an exoplanet which David Fossey describes as a hell whose properties defy the imagination. One of its surfaces is fully exposed to the closest star, and so the temperature is 2,200 degrees. And so this leads to metal vapor, and this creates clouds around the planet. On the other side of the planet, that is to say the side that is hidden in the shadow, we believe that those metal vapors could, when they are close to these different poles, they could first of all be transformed into rain and then snow. And so this gives us a very fascinating vision. And so between these two poles, there is a transition band that connects the two zones. And we could perhaps discover temperatures around 100 degrees. And perhaps we wouldn't be able to we would be able to travel there without any too much difficulty. And so these conditions really inspire us and give us a vision of clothing that is one of symbiosis. That is to say, two elements that are ecologically linked. What we're interested in is the mutual symbiosis. In some symbiosis, one organism will overpower another. That's the case for some parasites. But this is the type of vision that we are really interested in. And so to give you an idea of what this experience would be at a Maison Gamma, we have conceptualized an immersive capsule that we're going to give you more details about later on. And this project is the account of a voyager in search of a new symbiotic relationship with the environment. And using technologies and concepts by Maison Gamma, the voyager will be able to adapt to Corot 7b using plants and local minerals and ensuring that they respect the mutual symbiosis. And so we took inspiration from Umwelt, the Umwelt concept, which is defined as which is defined by the German biologist and naturalist as an environment or a sensorial environment or the clean world with a species or a individual. And so we imagine this as being the emitter between the Voyager, the mediator between the Voyager and the Corot 7. And so So, for example, we have the magnetic zones that we are showing here, the thermal zone as well, or the vision of metallic vapors.
Du coup, pour expérimenter ces nouvelles visions,
And so, to experiment these new visions, we looked at the interface, and we can see that there are interfaces that seem to belong to the future. So we took clothing. We saw the clothing as a translator that enables us to interpret sensorial visions that we can feel as human beings. And so it transmits information, whether they're sound information, vibrations, temperature variations, and the body will be completely involved in this experience. And this would enable us to interact. Historically, man is in opposition with the environment, but here what we're offering is to go against this and to have clothing that enables us to have a total relationship with the environment. And in order to do this, we took inspiration from the Monchu and David Foss's approach when they offered their artistic vision of these exoplanets. And similarly to other artists, that provided illustrations in encyclopedias. We designed our own ecosystem, Corot 7b, so plants and minerals that would evolve depending on the conditions of this exo-Earth, and that would make it possible to then analyze the Corot 7b. And these this clothing is interaction with the environment, which and so this suit would be the intermediary between the environment of the planet and the Voyager.
une collection de vêtements.
So this is our clothes collection for people exploring Corot 7b. Now we'll let you enter our fiction. 2021. Émilie Salvati-Kilereno, Eliane Bocchi. Our Maison Gamma, it's a digital design studio experimenting around clothing for tomorrow, motivated by the age of fast fashion and its ecological and social and creative impact. They conceptualize new paradigms of clothing made of biotextiles and living material adapted to a hostile milieu. Despite the relevance of their ideas, technology, humankind is not ready to get outside of its habitual comfort. The project is deemed a fantasy that can only accompany dreams of spatial conquest of a few companies. So to protect its integrity, Maison Gamma is evolving discreetly, far from catwalks and showrooms, and gets closer to scientific community. 3021. humanity once more express its need to conquer and expand and colonizing a new solar system. Mars, the new Dubai, is an artificial paradise where the richer people live with scientific research groups. The moon is a spatioport where engines are developed to travel outside our system. Despite scientific progress, humankind and its environment are still threatened. Maison Gamma publishes its manifest, The Universal Code of the Rights of the Living and Biodiversity. It promotes a symbiotic vision of men and their environment. Progressively, the ideology expands in parallel with the group founds Terra One, a independent spatial agency with an open source encyclopedia that aims at referencing different habitats of the universe. People are watching out for Proxima b, the closest exo-Earths, Maison Gamma and Terra One, are faster than other agencies and launched the first engine. And they need a prototype to explore this planet. 30,021. The technical progress and efforts by Terra One had made it possible to find and reference many telluric planets that could be inhabited. You, living on Proxima b, dream about being a part of the adventure. You put on your Maison Gamma clothes and use the exploration assistant. You get to cohort 7b, one of the exoterres that is quite dangerous. I am Gamma, your assistant. I am incorporated in all the clothes of Maison Gamma. I was programmed to accompany people traveling the cosmos and exploring exo-Earth so that the mission happened in the best condition possible, thanks to the database made by Terra One that is composed of an infinite amount of telluric planets. I am able to help you get to know the environment surrounding you. I will suggest the best options to adapt to the environment during your mission. You are entering the unicorn system and you get closer to cohort 7b. Be careful. You may feel shaken because the magnetic field is not stable because of volcanic activity. You need to know that there's a chance my system will not function once we get to the planet. Don't be scared. You will be able to use all my services once we are on the planet. And once you start exploring, I recommend you use plants and minerals from this planet, so we will be able to build the Maison Gamma clothes that you will need to explore the planet in these extreme conditions. Be careful and respect the Article 3021 for the living and all the recommendations about local resources, and respect the symbiotic norms. You have 2 minutes left to use the protocol, to follow the protocol and put on the clothes. Enjoy your travel.
Alors, comme je vous le disais un petit peu plus avant,
Like I said before, we have imagined these immersive capsules and we did it in real life for our diploma. The different visions were projected on the screen. So there are 3 screens on which you could try out the Maison Gamma clothes. We imagine different objects that could be worn, and that would enable us to interact with the different visions on the screens. So this is a first prototype of shoes to explore cohort 7b. They're very heavy. It's almost 1 kilogram each, but you feel quite light when you wear them on because of the materials that we use. There are different sensors on the shoes that help you play in real life and control the stability of the soil, for example. This is the first vision of cohort 7b, the magnetic vision, and the experience of the ground through the video.
Une partie.
Landing, done, no problems. You can start the exploration of card 7B. Just feel this new space. The volcanic activity of card 7B has an impact on the magnetic field. The ground is unstable because of that. It's not easy for you to explore your surroundings because of this instability. The particles are moving around you, and you can control the intensity of the magnetic field. If you move your feet, the particles are moving, and when it is stabilized on the ground as if you were walking, the ground is as stable as it can be. In this vision, the whole environment is modified, and we would like to create a system to stabilize at a local level, so that is in a 5-meter parameter around the person. And this is what you can play with. And it will be possible to download it soon. So if you just have a phone or a computer, you can play with this soon. So about the experience, the idea is to get to the next level, to meet every time new plants, and to respect the symbiosis that we talked about. So to get to a complete symbiosis with the environment. Thank you very much. Thank you very much.
Et, le projet aussi Gamma 30021 sera à la Paris.
The project will be presented at the Paris Design Week in September, from September 13 to 16, on the 14th, I think. If you want to talk with us about this, we will be around until 5, or you can send us an email or DM us on Instagram. And we were very happy to be with you today. Thank you.
Merci beaucoup.
Thank you.
Je vous en prie. Alors, eh bien...
Wonderful. Now, all of you will be able to write your messages, and these messages are the messages you would like to send to Extraterrestrial Intelligence. I will give the floor to Julia Goodkin-Guanfolo. She is a scientific mediator at the Cité des Sciences, and she will explain everything to you. Julia, maybe you want to say a few words about what messages were sent in the past, right?
Alors,
And so it seems to be working right away, which is fantastic. Good afternoon to everyone. My name is Julia Goutin, and I'm a scientific mediator at the Cité des Sciences et de l'Industrie. And indeed, I suggest that we have a talk about the different types of messages, interstellar messages that we could send into space that may be interesting to share. So that eventual life forms, intelligent life forms or aliens can detect them. And for this, we will be using a digital tool which is called Mural. It's a type of a big virtual post-it note on which you can write your own messages. I'm sure you have a number of ideas. And so we will share this link with you and explain how it works. It's very simple, you'll see. But before that, I would just like to give you a reminder, an historical reminder of the messages that have already been sent into the universe from our planet. Because for decades now, we have been regularly sending messages. So, sending messages into the universe, I'm sure you will undoubtedly realize that it means that there are a lot of ethical, political, linguistic issues that arise. It can also be dangerous. So there are many questions that we're asking ourselves, and we're going to talk about this later on in our roundtable. But what I'd like to do is just to give you a historical presentation of the messages that have already been sent. So this desire to want to signal the presence of human beings to potential life forms beyond Earth is not new. Since the 19th century, great physicians have thought about the different scientific systems that sometimes are very elaborate that can be used to send signals. Nikola Tesla, for example, Carl Gauss, large physicians from the 19th century, offered systems that would send electrical charges or light signals to try and send a signal from our planet. Then we also had more original ideas, such as, for example, to use the large forests that we have and to cut geometrical shapes in the Siberian forest, for example, to chop trees into triangular shapes, for example, to illustrate or to represent Pythagoras' theory, for example. So there are so many ideas that didn't come to fruition. However, as of the 20th century, we really started to send messages. And it all began during the Cold War. This was a time of competition between the Soviet Union and the United States. As you will know, it was a race to the moon. And the Soviets were the first one in '62 to send a message to Venus, which is not too far from Earth. They sent 3 words. The word peace, Lenin, and URSS. Let's not forget the historical context. It did take place in 1962. And a few years later, in 69, the Americans sent a message, and they also landed on the moon. That was the first Apollo mission, so Apollo 11. So July 69, where they erected a commemorative plaque which attests the presence of human beings on the moon. There is also an image with the 2 hemispheres of our planet. So that was the Americans in 1969. So these 2 examples, as we understand, are more symbolic than anything else because the moon and Venus are very close to the Earth, and it's undoubtedly not there where we will find life forms that would respond to us. It was symbolic to demonstrate the technical prowess at the time, but the decision was made to go further. Therefore, in 1970, in 1972 and 73, we sent probes that flew past Jupiter to the gaseous planets, and on board these Pioneer probes there was a plaque, and you can see it here, and this is a material message that we sent. It's a very small plaque. It's smaller than an A4 piece of paper. And so this probe left in 72 and 73, and we can see here there's a representation of the woman and the man. We also have our solar system here at the bottom with Earth's position within this solar system. We also have here the sun, which is well positioned as it relates to the references we use in astrophysics. Pulsars, we have 14 reference pulsars, and we have also identified where our sun is located in the middle of these 14 pulsars, and then we also have the hydrogen atom representation here. So these are signals that we sent in 1972 and 1973. Material, physical message that we sent to space. And we have lost contact with these Pioneer probes, but they, I'm sure, continue on their trajectory into space. The next year, so in 1974, humans decided that we needed to go much further than our own solar system, with an aim to contacting intelligent life. And so the idea was that we would dematerialize messages and to use electromagnetic waves, in particular radio waves. And within those waves, we could use coding, so zeros and ones, to send those messages. We sent the Arecibo message, so that was in 1974, and that was sent from Puerto Rico. And this is the message. So if we were to decode the binary message, so we sent the numbers from 1 to 10. Here we have the 5 physical elements that are important for life: hydrogen, carbon, nitrogen, oxygen, and phosphorus. We also sent chemical formulas, and we have here a DNA helix, which is represented in blue. We have here the number of human beings on the planet at the time, so that was over 4 billion in 1974, and here we have a representation of Arecibo, the telescope. And so this was a message that was sent to a star cluster, which is very far away, 21,000 light years away. So a radio wave that travels at the speed of light would take 21,000 years, so we shouldn't be in a rush with this Arecibo message. And if anyone detects this message and they decide to respond, we would have to wait another 21,000 years for that message to return. So it's really a bet. And a final example that I can present to you. At the end of the 1970s, in 77 specifically, there was another probe that was sent into orbit and towards the gaseous planets. And a little bit like the Pioneer plaque, there was a gold disc. Here is the gold disc. And what's very interesting about this gold disc is that a lot of information was included, images, hundreds of images that are coded in binary language, images of our planets, humans, different monuments. We also included 12 minutes of terrestrial sounds, so the wind, the sea, many things. And we also included music, 90 minutes of classical music and modern music. We included lots of things, and we wanted to maximize the chance that they would enjoy that music. We have the word hello in different languages on that disc. And what was very interesting with this as well is that on the disc, on the gold disc, was an engraving of an explanation of how to decode and to read the information on this Voyager disc. And so this was sent physically into space once again, and this took place again in the 1970s. Since then, we've regularly continued to send messages. And of course, the president of METI, who is with us here today, will be able to talk to us more about this later on. But most recently, in 2007, there was a sonar calling. There was a music festival whereby 33 musical tracks were sent to a source that was a lot closer than the 20,000 light years that I mentioned earlier on. We aimed at a star which is 12,000 light years away, and it's an exoplanet, as we mentioned earlier on, in the habitable zone, and so that's a lot closer, and it means that we're able to target potentially habitable exoplanets that are closer to Earth. So that was just a quick rundown of the messages that have been sent, and now it's up to you. Over to you to suggest the messages that you would perhaps like to share. What do you think would be interesting to send into space? And so to do this, my colleague is going to show you how to use Mural, which is the software, and we will send this link via the chat in less than a minute's time so that you can inscribe your message. But before that, let's explain how it works. So you click on the link, and this will take you directly to the Interstellar message page, and all you have to do is double click, and you'll see a post-it note pop up, and then it's down to you and your imagination. So it says here, hello aliens, And of course, you can be more original if you wish to be, or not. And you can change the color, you can change the font, you can change shapes. And you'll see it's very intuitive, very easy to use. So please don't hesitate to have a play around with a mural. And if you're able to draw something, don't hesitate to draw something. Or if you have a photo to take, then take a photo. And you can also import that photo directly. Just like this beautiful drawing that Mark did for us. There we go. So on Earth, we live in houses or in buildings. So I'm sure that you will also have a lot of messages that you would like to share. So there we have it. As you can see, it's very intuitive. You can zoom in and zoom out. You have a space in the bottom right-hand corner that enables you to see the entire working space. So please do not hesitate to inscribe your messages. We are counting on you. And at the end of the day, Mark will give us a rundown of the different ideas that you have come up with and the things and messages that you would like to send to potential life forms in the universe. So now, I will conclude here, and we will be back after a brief video from the planetarium. Thank you very much. Sponsor one of the chairs at the planetarium. And take part in the renewal of this emblematic place. High definition, spatialized sound. An international reference.
Donc c'est maintenant le moment du...
And now there will be the second art break. Margot Hervé Berdis and François Robig are invited on stage. They graduated from FEMIS in 2020. Their work was about making a movie on an exoplanet. Hello. Thanks to all of you for being here today. We are François and Margot. We just graduated from FEMIS. It's a cinema school in the 18th arrondissement, and we're happy to share with you our movie Exoplanet that is a partnership with Micros for the Observatory of Paris. We'll show you the movie. Sorry, we were not able to use the rights for the music, so we'll just show you the pictures and then we'll tell you a bit more about why the observatory ordered this video and how we made the movie. Can you please roll the video?
Merci beaucoup.
Thank you very much. Unfortunately, we were not able to use the music. It was electronic music. So it was an order by the Observatoire de Paris by Stéphane Rasvé. Every year, in third year, famous students receive a planet. And the idea is to make tangible scientific data and build a set for the planet. This was exoplanet HD 219134b. It's an exoplanet where temperatures are 700 degrees on the surface. It's very close to its star. And on the surface, there are crystals, diamonds, and a lot of sulfur. So it was interesting to work with the observatory to get the scientific data. And we would not to make a very realistic presentation of this data because from a cartographic point of view, it wasn't that interesting. We wanted to have some freedom. And of course, we agreed with the observatory not to make something completely crazy. In real life, actually, we would not see anything on this planet. So we tried to show things that we are unable to see on this planet. It's quite interesting to work in the cinema industry with this relationship between realism and creativity and imagination, really. And it was really about imagining what's on this planet. François, do you want to say a few words? Yes. Hello. Maybe I could add, and you mentioned it, we are students, decorator. So we work on decoration, on sets, if you want, for the cinema industry. So this time we had to work on this topic and make a movie for the Observatory of Paris. And Margot, you mentioned it, it was a partnership with a company of visual effects. It's called Micros Technicolor. I think it's the biggest special effects company in France, if I'm not mistaken. And it was really a learning experience as a decorator for us. We had to imagine what we would build and what we shouldn't build. Where does building objects on a set stop? And where does special effects begin? So we really had to think this through from the beginning. So we made a storyboard first, and we needed to think about what camera movements we needed, what plans would be shot, and so on. At Femis, there are few movies that are interested in this issue of special effects. There are very few genre movies produced at Femis, this kind of movies, because special effects are actually really expensive. So for us, as student decorators, it was very interesting to think about these issues. If you want to speak, Margot, please don't hesitate. Yes. I think what's interesting is that storyboarding is about scale as well. When you represent a planet, there are things you can represent with a set. It was a scale 1 where you saw the material, but with the cliff, it was a mix of a set that we built and then what is called a green screen, and we implanted the special effects because obviously it was too expensive to create 2,000 meters of horizon in a studio. We don't have the means to do that, a whole skyline. So what was too big at scale was special effects, but the close-ups usually were some objects that we built. There were other effects as well. The fumes, for example, it's SFX. So that's the effects you add in post-production. So basically what you watch were pictures with a set at scale 1. It was a huge cliff that we built with a 4x4 bed of rock, if you want. And that's the set where the astronaut, Margot, walked, and we built a second set. And it's one of the last shots of the movie. It's the crevice in the movie, and it was a 7-meter set that we built. And the last shot, and I think that something that was quite visible, you see that the planet is really small in front of the sun, and obviously this was 100% digital. So it was really about thinking about how we could organize all these shots. What do we build? What doesn't need to be built? Where do special effects start? This is 100% special effects, for example. Or how do we see the depths that you saw in some of the shots? So we wanted to think about all these shots before shooting. Obviously, we had to keep in mind what effects we wanted this set, it thought, to be filmed like this, if you will. Everything was thought about in advance, and it's not really possible to film it and to shoot it in any other way. I think we've said it all, I think, Margot. Maybe a few words about how to prepare for that. To present an exoplanet, you need to work a lot in advance. We only had 2 months to do that. And there's a whole team of sculptors and the people working with resin and with plaster, and the cliffs were polystyrene. So really, there were many people working on the project, and the plaster was an important part of the set. So sculptors worked a lot, and then the cameras came in, and obviously lights. There were other students working on this project, and in post-prod, I think we had 1 month. Yes, it was quite interesting as a decorator. We were very invested in special effects. It's something that we don't usually do. Special effects, decorators usually don't deal with these effects. So our department directors really wanted us to be able to understand that special effects in a movie is usually the last layer, the last visual layer of a movie, and maybe the finishing touches. It was very interesting for us to be able to see that side of a project. And I think we learned a lot from this. Do you maybe have questions or?
Alors, peut-être, oui, on a peut-être.
Maybe we can have one question. Does anyone have a question in the room? Well, wonderful. Someone at the front. Well, congratulations for your work. I just wanted to know what your work will be used for. Every year, the Observatory of Paris asks FEMIS for a movie. Is that how it works? So I would like to know what happens to the movie once it's done. What is it used for? Is it some kind of informative movie? It's just for aesthetics? What does it become once it's finished? Yes, it's something that they usually use for them when they organize conferences, workshops. They actually use these movies. From what I understand, talking with Stéphane Masbé, these movies are an opportunity for him to talk about the representation of exoplanets and of other planets. maybe I will betray the way he thinks, but what he's saying is that we see many pseudo-scientific images, and usually the aesthetics is very perfect, and it is mixed with the photographs that we have from space, and it's usually not very sexy, it's usually black and white. And I think what he wanted with this work is to do another kind of interpretation, to really interpret scientific data. And when he screens this in one of the workshops, what he says is that even if this seems completely crazy, it's not crazier than the standard images we get of exoplanets that are completely wrong, but that actually look real. Yes, the idea is to not lie, to say, okay, this is a graphic project, it's not real life, and he really wants to make a difference between scientific pictures and the idea we have of other planets. Different exoplanets are chosen every year. One time it was Proxima b. Maybe you can go to the website of the observatory and take a look. Yes, I think so. One other question? Thank you very much. Thank you very much.